We are live now. You can start.
All right. Right. Hello, everyone. I'm Mikailu Nadro, and the topic of today's workshop is Hacker Dojo Project Research, which is inner product arguments. But before we go further, I'd like to introduce Dora Dojo. So the question is, what is Dora Dojo? Dora Dojo is an open source knowledge community focused on cutting edge technologies such as encryption and Web3, co-built by hackers. So DoraHacks regularly organizes knowledge-sharing sessions in the form of live broadcasts, audio, and text. So the topics covered include the L1s, L2s, consensus algorithms, architecture, and related content in GitHub reps. Some of the specific topics covered include the scroll or polygon, ZKEVM, we have the aging hybrid, we have stackware aspects, optimism as well, Zekri, Aptos, Move, and cryptography. We also have under cryptography we have things like zero knowledge proof, ZKPs, public key, hash functions, and lattice ciphers. And we also have distributed systems, Ethereum protocols, and many more. So that's the overview of DoraHacks, and it's very important to know where it's hosted on. It's hosted on DoraHack.io, DAO Bounty. Let me take us quickly to all right. So these are here are current bounties that are currently going on. We have Codex, Akadojo, Akwe, we have Aptos, VK, and many more. So interested participants can come and participate in any of these bounties and claim it. All right. So this brings us to the topic of today, which is inner product arguments. And we are going to take it in 3 points. So the outline, the first point is we learn about the fundamentals of inner product arguments. Then two, the principle and practices of vector commitments using inner product arguments. And finally, we'll be taking the comparison. We'll compare the difference between Pedersen commitments and the KZG commitments, which are the two most common ones. All right, so this takes us to the next, the fundamentals. All right, what are these fundamentals here? We'll take a brief introduction. So, supposing you have some secret information, let's say passkeys, the two lockers encoded in a couple of vectors, let's say A and B, then you, the prover, let's just take an example, you are the prover now. You want to convince the government, let's say the government is the verifier, that you are the owner of these lockers. So you naturally would have to prove that you know the vectors A and B, but you cannot reveal them because of obvious reasons. So can you prove the knowledge of A and B without revealing them? It's a tough question. So now, the inner product argument lets you to do such that the government will be convinced about your ownership without knowing about your secret. So basically, this is just kind of like an introduction, or let me say, rather an overview of what product arguments are. Inner product arguments are all about. Next. So inner product arguments are a particular type of zero knowledge proofs and allow a prover to convince a verifier that the inner product of two committed vectors equal to a public scalar. We'll be looking into that as well. The main efficiency parameters for them include prover complexity that measures the time complexity to generate a proof. Communication complexity that measures the proof size. And then we have the verifier complexity that measures the time complexity to verify a proof. So we have all these three complexities to help you and help a verifier to get to verify a particular proof without actually knowing what it is. Okay, so we have effective tools to reduce complexity of many other cryptographic primitives, such as we have the arithmetic circuit satisfy and we have the polynomial commitment schemes. Okay, so the first step, first one we're taking is the bilinearity, which is the inner product is bilinear, which means that it satisfies the following properties. So the linearity um, is the first argument, and the first argument is followed by this equation: AU plus BV of W, which will be equal to A of U of W plus B of W. And the second argument, which is the linearity in the second argument, is followed by this equation: U of AW plus BV, which will give you a result of A into bracket U of V plus B into bracket of U of V. Then symmetry, second point. The inner product is symmetric, meaning that UV is equal to V, just in simple terms, for all vectors U and V. So let's go to the next. The third point is positive definite. That means the inner product is positive definite, which means that the UU in this case is greater than 0 for all non-zero vectors. And we have U equal to 0 if and only if the U is the 0 vector. That's the only time you get it to be equal to 0. And this property ensures that the inner product can be used to measure the length, that's the norm, of a vector and also an angle between two vectors. So the fourth one is orthogonality, which is two vectors we have U and V are said to be orthogonal if the inner product is 0. So that is, you have UV equals 0. So these are orthogonal vectors. And it's very important in many applications as well. Uh, an example is used in conception of autonomous basis. And the fifth one is the Cauchy-Schwarz inequality. So one of the key results of the inner product basis is the Cauchy-Schwarz inequality. This is one of the most important ones. This says that for any two vectors UV would have UV less than or equal to U and V, where U and V represent the norms as the length of the vectors U and V respectively, where the U here is a length, while this V here is also a length, each representing lengths of vectors. Then the sixth one is the inner product spaces. An inner product space is a vector space that fits an inner product. The inner product provides the notion of angles and lengths within the space, allowing for the development of various mathematical techniques and results. This is actually highly applicable, I think. So now, an inner product denoted by UV or UV or UVS is a bilateral, symmetric, and positive definite functions, which were all mentioned earlier, that takes two vectors, usually denoted as U and V, in a vector space and produces a scalar value, which is the result. Now, the inner product of the two vectors UV is typically defined as we have UV plus V. have u equal u suffix 1, v suffix 1 plus u suffix subscript 2 multiplied by v suffix 2 plus down to whatever the maximum number is. That's what this n is representing. It could be up to 100 or more. So where u1, u2, and of course the maximum number we don't know. So depending on what you are using it for, if it's up to 100, you just replace the n with the 100 by saying 1, 2, 3 down to 100. And then we have the v1, v2, the same thing, vn, depending on the number you're stopping at or the limit. Are the components of the vectors u and v is dc. So now we look at the polynomial commitment schemes form of a fundamental building blocks in many modern argument knowledge in this scheme. A prover can construct a commitment to polynomial. We mentioned earlier that polynomial is one of the ways of looking at it, and also an arithmetic linear equation. Right. So I think we just go to next. Okay. We present a univariate polynomial commitment scheme, which is set up, commits, open, and verify open, based on the multivariate scheme of which is itself a variant of the inner products argument. We first presented in the adaptations from the black group. So first one is given as given degree bound d minus 1. We define a set of 1. We have lambda here. That's the power of lambda, then d. An algorithm that produces a common reference in the standard deviation equals GFP, where G is for G of prime P is random G D and G is power of D. Right? So let's commit be defined as we have the standard deviation sign here, P of X and of R equals to A multiplied by G plus the R H. For binding factor R, where A suffix I is of F, that's the suffix of F subset rather, is the coefficient for the I degree, the term of the P of X. And then following all these equations, we have one, we commit E. So this is the Pedersen vector commitment to the polynomial coefficients. And we mark that such commitments are perfectly hiding and additive homomorphic. We have VA, B, R, S, E of F, then the PX, QX, E of FP, and X. So this is what we would have. This equation over here plus B is going to give us commit of these equations here, which was earlier mentioned over here, which are the commitments now. We have them all into the bracket. So we have a setup, open and verify open by a PSHVZK as a ZK argument of the knowledge for relation. So we have a curly bracket here, P of X of V to the bracket A of R. We have P, we have A, P being a function of A and G plus R, we have H and V, which is also equally give us this equation as our commitment over here as well. Not forgetting that for the commuted polynomial, we have a maximum degree d minus 1, clearly stated here in the power of x. Okay. We have zero knowledge proof argument of the ZKPs allow a prover P to demonstrate knowledge of a witness W such that you have X W as a subset of R for a polynomial term decidable relation R on some statement X without revealing any information about W to be verified, which is just the basis of what the inner this thing does, the inner protocol does. So you have some of the information embedded. The verifier doesn't actually have to check to know all the details, but this would allow him to kind of verify if the information is actually true without revealing the basic information about it. So we write relations in form of statements, witness, then predict. Now we will work with arguments of knowledge which assume computational bounded provers. We will model P, V as interactive algorithms with a preliminary algorithm setup that produces a common reference string of this. We will denote the transcripts of the interactions as the bracket P, the standard deviation XW, have V, standard deviation X and P, then we verify internal randomness P, sometimes being omitted. Yeah, that's this one in particular. Sometimes think it's negligible, that's why sometimes we just eliminate it. Then for definition one, we have perfect completedness for setups PV. So here's the equation right here. It always equals to 1. The next one is going to be a negative lambda less than or equal to, right? And then we have the definition 3, 4, and 5. All talking about similar stuff. For the 3, the setup PV, um, argument of knowledge, it has a perfect completeness and computational witness extension emulation. So the fourth one is a public coin argument. If the verifier chooses their message uniformly at random and independently of the message sent by the prover. So this could be for this in this case, and for the fifth setup for the PV, perfect special only verify zero knowledge is for all non-uniform polynomial term adversaries. That's A subscript 1 and A subscript 2. And polynomial decidable relation R with X and W, all being subscripts of R. Therefore, I use a probabilistic polynomial time simulator such that this particular equation around here, where the P is the verifier's internal randomness and so the bottom line is it all comes down to what the commitment is being given of as the output over here, right? Okay, so we take the second point, which is principle and practices of vector commitment using inner product argument. First one is vector commitment is a cryptographic. First, we look at what it is. So, vector commitment is a cryptographic primitive that enables one party to commit a vector of values without revealing the individual elements in that particular vector. The commitment should be hiding, meaning that you should not leak any information. So if you can recall, that's the main aim of this inner product argument. So It should not leak any information about the vector's contents, and it should be binding, meaning the committer cannot change the vector once it's committed. You have to be careful because it can't be changed once it's done. Okay, so second point, inner product arguments are, well, we're just going briefly defining them again. So the inner product arguments are mathematical tools to prove statements about the inner products of two vectors revealing have two vectors, so rather, I'm sorry, without revealing the vectors themselves. And they are based on the properties of inner products, which are bilinear, meaning they satisfy linearity with respect to addition and scalar multiplication. I think we've seen all these things earlier. And the commitment scheme now typically involves a commitment phase and a proof phase. The committer first commits to their vector of values using a commitment function. It takes the vector as input and returns a commitment. This was also mentioned earlier. So what it does is it first uh, commits the vector value using a commitment function without revealing the actual details of where it is for the verifier. And then it takes the vector input and then it returns it as a commitment. This goes further to prove that the, the verifier can trust this even without knowing what the information is. So in the proof phase, the committer can prove statements about their committed vector without revealing the actual vector value. So what are the properties of this vector commitment? We have three basic ones. We have hiding, binding, and knowledge soundness. So the commitment should be hiding, which means you should not reveal any information about the committed vector's contents. That is one. The second one, the most important one, I think, is the commitment should be binding, meaning that the committer cannot change the vector after it's been committed. And the last one is the knowledge soundness. The committer should not be able to generate fake proofs without knowing the committed vector. Okay. So all these are the properties of the vector commitment. Then what are the applications now? So vector commitment with inner product argument has applications in various cryptographic protocols being used. So for example, it can be used in confidential transactions in blockchain. I know this is being used currently. It's also used in privacy preserving smart contracts on the blockchain as well, and more. And the other application is in security. Vector commitment schemes using inner product argument should, should be designed to resist various cryptographic attacks, including attacks on hiding, binding, and zero knowledge properties. Okay, so this takes us to our last point. Compare the difference, uh, comparing the difference between Pedersen commitment and the KZG commitment, two most commonly used ones. So here is kind of like a play. So we have the commitment scheme, security assumptions, proof size and verification, where we have use cases and performance and efficiency. Performance and efficiency are always mostly together. So first one we have a commitment scheme, right? So the Pedersen commitment. So these are actually the basis of the comparison, comparing the differences between these two, the Pedersen and the KZG, right? So we're starting with the first, which is the commitment scheme. Let's see the differences between the two. First, you can see Pedersen commitments are based on the Pedersen commitment scheme, obviously, which uses modular arithmetic and hides the committed value using discrete logarithm problem, that's the DLP. The commitment, which can be stated as C, they stated it as their commitment is equal to C, and the equation is G to the power of M multiplied by H to the power of R, where G and H are publicly known generators, while our M is a value being committed to, and R is a random value. So what about the KZG commitment? The KZG commitments are based on the kit. Well, this is full meaning of KZG. Kit is Verucha Goldberg. Permit me if I pronounce it wrongly. Polynomial commitment schemes. So the KZG commitments, they use polynomial interpretation. It's different from what Pedersen, which uses arithmetic and modular arithmetic. So they use this polynomial interpolation and to evaluate rather and evaluate. So they use polynomial interpolation and evaluation to create a commitment. So the commitment is formed by evaluating a polynomial at a specific point and revealing the resulting value and also a proof. The second point of comparison is security assumptions. So the Pedersen commitment, it relies on the DLP. We mentioned this earlier. It means discrete logarithm problem, which is a well-studied and widely believed to be hard mathematical problem. The security of Pedersen commitments depend on the interactability of the DLP. So while the KZG commitments rely on the hardness of polynomial interpolation and evaluation problems, right? So the third one is proof size and verification. So the Pedersen verification, verifying a Pedersen commitment is efficient and the proof size is relatively small. The verification involves checking that the commitment value and the random value R, which was earlier stated here, are used correctly in the commitment equation. Just have to be very careful that it's being used correctly. In the KZG commitments, they come with larger proof sizes compared to the Pedersen. So verifying the KZG commitments can be more computationally intensive, obviously, because they use the polynomial extrapolation. So they take wider um, sizes, right? So fourth is the use cases. What are their use cases? So the Pedersen commitments are commonly used in privacy preserving cryptography protocols, such as confidential transactions in cryptocurrencies like Monero. Monero blockchain uses these, and while the KZG are often used in polynomial commitment schemes for zero knowledge proofs. They have applications in verifiable computation, decentralized identity systems, and more. Obviously, because it uses the ZKPs. And I think the final one is the performance and efficiency. So the Pedersen commitments are known for their efficiency and have been widely adopted in cryptographic applications. They provide a good trade-off between security and performance, while the KZG commitments, due to their larger proof size, may be less efficient in terms of bandwidth and computational compared to the Pedersen, right? So in conclusion, the Pedersen commitments and the KZG commitments are two different commitment schemes with distinct security assumptions, use cases, and also performance characteristics. The choice between them depends on the specific requirements of a cryptographic protocol and the trade-offs between the security and also for efficiency. I hope we, we could learn something from this presentation of today. And this brings us to the end of today's presentation. Thank you very much. And for further references, got some material from Sean Bao, Jack Greek, and Daira Hop. This is a material released in 2019 by Electric Coin Company, and also one from Suyash Bhagat in 2020. Here is the links all below. Right. So thank you. Thank you. Okay.
Oh, thank you. Goodbye.
All right. Goodbye. Thank you.